Hi again, everyone. We've just heard from Shui Chen about extreme precipitation events as observed by satellites. So next, I'm going to give you an overview of how extreme precipitation changes in response to global warming. I won't introduce myself again, since I should have already done that this morning, but let me cue up my slides here. So, my approach to thinking about extreme precipitation starts from thinking about the distribution of precipitation in terms of its intensity. Starting from a histogram of precipitation intensity like we see here, say hourly or daily accumulated precipitation. In response to global warming, we generally expect the distribution to shift to heavier rain rates as well as changing its shape. So you can see that going from the brown current climate to the green new climate in this schematic here. Even though we often think about precipitation and especially extreme events as discrete phenomena, there's a lot we can learn about them starting from the biggest scales, from the global scale. So on the left here, these are some results from climate model simulations that are forced by increasing greenhouse gases and changes in aerosol forcing from a few generations of CMIP ago. In these simulations, the amount of water vapor increases by about 7% per degree warming, which is just to say that relative humidity doesn't change very much. Now, even though precipitation is a flux of water, the global mean precipitation increases much less than this, just 1 to 3% in these same simulations, which we can see here on the right. Even in the most recent generation, these results haven't changed very much. In fact, I recently checked. So what we call this kind of muted increase in global mean precipitation relative to the change in water vapor is an energetic constraint on global mean precipitation. And so now that happens because global precipitation is not just a flux of water, but it's also a flux of energy through the climate system. So precipitation can only change as much as other aspects of the planetary energy budget give it space to change. But this also turns out to be important for the whole distribution of precipitation, not just the mean precipitation. So now if we step forward a little bit and scale out to one view of the distribution of precipitation, a slightly different one. Now we've got cumulative percentiles of precipitation on the x-axis. So more extreme events occur as you go further to the right along this percentile axis. So what this is showing is the changes in the precipitation events at these different percentiles of the all-day precipitation distribution, and how they change in response to warming in the CMIP-5 generation of climate model simulations. So on the very left here, we've got these changes in global mean precipitation that are really similar to the ones that we saw on the previous slide. And then as we move to the right, as the events get more extreme, the multi-model mean also increases. And as you get to the heaviest events in the global mean, what you see is that these events increase at a really similar rate to the increase in water vapor in response to warming. And so that's something that has been pointed out for quite some time. The rate of increase of these events goes up as you get to more and more extreme events. Also, the uncertainty across models increases as you go to more and more extreme events. Now, this isn't just something we see in model simulations. It's also something that's been observed. So this paper by Seong-Ki Min and colleagues from 2011, so already almost 10 years ago, found that human-induced increases in greenhouse gases have contributed to the observed intensification of heavy precipitation events over approximately 2/3 of data-covered parts of northern hemisphere land areas. So this isn't something that is just projected by climate models, but it's also something that we've already observed. So extreme precipitation increase is already happening. But as you can see from that quote, it's not necessarily happening everywhere at the same rate. So there is a spatial pattern of extreme precipitation change that is projected by climate models. It's not all this increase at constant relative humidity warming the same rate as water vapor. So this is the maximum day of precipitation each year, the intensity of that event each year. and its percentage change with warming. And you can see that it's relatively uniform over a lot of the mid-latitude regions. There are these regions in the tropics where you get these big increases, and that's because of shifts in the ITCZ. You can also see these regions where you actually have a decrease in extreme precipitation. So you can see that that's just hitting the very coastal region of Southwest Western Australia, these subtropical stratocumulus decks in a lot of the eastern ocean basins, and extends all the way into the Caribbean as well. So there's a spatial pattern of this, and this nice study by Stefan Thal in 2017 showed that this can be explained by changes in circulation. So I want to tell you a little bit more about that. Now, I want to go through this one piece at a time, and we're going to start at the end here with the part that looks the hardest, but it's actually the simplest. So this is called the thermodynamic component of the extreme precipitation scaling. And so what this is it's just condensation along a moist adiabat. So it's the change in the saturation vapor pressure with pressure. So that's just the vertical coordinate. And it's evaluated on a moist adiabat. So it's at constant moist potential temperature. Okay. So the thermodynamic part is something that depends only on temperature and its vertical structure throughout the atmosphere. And so that's actually a pretty straightforward thing to quantify. And now that increases with warming just a little bit below the amount of, at the rate below the amount of moisture that you can have in the atmosphere. So that's 5.5% per degree Kelvin or so. It depends a little bit on what temperature you're at. Okay, so that's relatively straightforward, and climate models actually agree pretty well on what that quantity is, what its magnitude is. Now the second part is something we call the dynamic component. So this is the vertical velocity. So omega is the pressure vertical velocity. Now taken together, the dynamic part, the circulation, and this thermodynamic part tell you about the vertical moisture advection. And we're just assuming that anything that gets advected up and then condenses immediately falls out as precipitation. So that dynamic part, you have that initial vertical velocity that varies in space, and the way that changes with warming depends on where you are on the planet. And that also is something that's a lot more uncertain, and we'll get into that a little bit more in a minute. Now this final part that I want to emphasize here is called the efficiency. And so that's kind of a scaling, and it can represent things that are at smaller scales that aren't necessarily represented explicitly in the climate models. And that's going to come up later in Jiao's talk. Okay, so now that we've got a little bit of an idea of this dynamic and thermodynamic component that can go into the extreme precipitation scaling, these are quite accurate, then we can go back and think about what that means in terms of these different aspects of the extreme precipitation change that's projected by climate models. So in terms of the spatial pattern, this study showed that the spatial pattern is driven mostly by the dynamic part. So these changes in extreme precipitation are mostly modulated by differences in the vertical circulation and not by the thermodynamic component. Models agree reasonably well on that. Now coming back to this breakdown in terms of percentile of how extreme the events are, another thing that I want you to notice that I didn't emphasize so much before was this really large spread across models. It gets bigger as you go to more and more extreme events. So when you get to the most extreme events, you can see that in the global mean, some models have increases that are a little bit less than this change in moisture in response to warming, and some of them have increases that are more than twice as large. And this is just the interquartile range. It's not the full range across the models. And so there's quite some spread in the magnitude of extreme precipitation change. And a lot of that spread is coming from the tropics rather than the extratropics. And so there's some pretty interesting things that happen with that. Oh, and those changes are driven by dynamics, and sometimes perhaps by efficiency, but they're not driven by thermodynamics. These differences across models aren't driven by thermodynamics. Okay, so now getting into what that can mean for other aspects of the precipitation distribution. So Chad Thackeray, who is in Alex Hall's group, published this interesting paper a couple of years ago where one of the things that he showed is that these models that have larger increases in extreme precipitation in response to warming, this one's over here, also have smaller increases in non-extreme precipitation. So what this is showing you is this manifestation of the global energetic constraint. If you're going to have larger increases in extreme precipitation, and it's the case that those extreme precipitation events actually contribute a substantial amount of the total precipitation globally, then you have to compensate for that by smaller increases, or even in some cases decreases in the non-extreme precipitation events. So I think this is pretty interesting. So in schematic form, if in the current climate, we've got some big extreme precipitation events, say in the tropics, and then we've got these smaller non-extreme precipitation events, and probably more of them, in the current climate, then in response to warming, the models show that there are a range of ways that the climate could change, which are perhaps plausible. In some of the climate model simulations that have less of an increase in extreme precipitation, they also have more increasing light precipitation events and moderate precipitation events. Whereas the models that have larger increases in extreme precipitation have less increase or even decreases in the non-extreme precipitation. So the whole distribution of precipitation is really tied together by these global energetic constraints. So how do we know which end of the spectrum we're headed for? There are a lot of reasons why that might be, and it's a really active area of research, trying to figure out what kinds of changes are physically plausible, and also which ones might be correct. One thing that is kind of the talk of the town is increasing model resolution. So the coarse resolution of climate models that we're running kind of conventionally most of the time today, they're missing a lot of the mechanisms and a lot of the phenomenon that are happening at these smaller spatial scales that they can't resolve explicitly. And so we're starting to see more models that are able to resolve convection. Weather models are already at a much higher resolution than climate model simulations are. But those don't have the need to run for a really long time to sample the full natural variability, which are really important for quantifying the risk of extreme events. So we're moving toward having global cloud resolving simulations, but we're not ready to do that all the time just yet. We're just starting to be able to do that a little bit experimentally. But as I've been pointing out, we've kind of got a few different things that we need to balance here. We really want to know what the impact of these global energetic constraints are, but we also want to be able to resolve the individual phenomena as much as we can in order to capture these extreme events as accurately as possible. I don't really think the right modeling system exists yet. So in the meantime, we're just piecing together the information as best we can from what we have. Now, something you might have heard about in the news is event attribution. So we know that extreme precipitation events are already becoming more intense. And so a lot of times when there's a specific event, one big example was Hurricane Harvey a couple of years ago, people want to know how much more precipitation occurred within a specific extreme event because of global warming, how much would have occurred without global warming. And so there are a number of techniques that people use to do this now. And the part of that we're a lot more certain about is this thermodynamic component. And then we know that there can be modulation from the dynamic component, but that's much harder to really put your finger on. But it's a pretty up and coming area of extreme precipitation research, especially because it's so popular in the media and people want to know what's going on. So it's in kind of a lot of demand. So with that, that's the big picture of some of the topics these days and how extreme precipitation responds to warming. So overall, it gets more intense. And this is mostly driven by a thermodynamic component of the change that's due to increased temperature and the increase in water vapor that comes along with that. There are changes in dynamics and potentially also in precipitation efficiency that could further increase or decrease extreme precipitation change relative to that thermodynamic change. And one of those possible pathways is through changes in convective organization, which we'll hear about from Jiawei Bao next, who's been doing a lot of really interesting work on that. So with that, I'd like to thank you for having me this week. And I just wanted to share these couple of pictures from summer institutes in the ancient past and of a successful whale watch trip from Lime Kiln Point. Talk to you again soon.